right, good morning, everyone. So we are on a third lecture on our MOOC course on distributed acoustic sensing, or DAS. And we continue with Philipp Weinmann from AP Sensing, who brings us back to how to read DAS data and make sense out of them. Philipp, the stage is yours now.
Thank you very much again. Good morning to everyone and welcome to the second part of my lecture, which aims at giving an introduction to the technology of distributed acoustic sensing. While my presentation yesterday focused on general aspects of glass fibers and the measurement concept of DAS in general, in today's presentation, I will dive a bit deeper into the physics of DAS. So in particular, we will see how the information of local strain, which is measured by DAS, how this information gets encoded into the backscatter light, which is detected by the DAS system. Since the DAS technology is new to many people, I think it makes sense to have a quick refresher of what was discussed yesterday. So I want to recap a few key points first and then address the two open questions from yesterday. The key points I want to summarize of first of all the measurement concept. We said that DAS works by connecting a DAS system to a glass fiber and thereby transforming the glass fiber into a microphone. That means we will be able to listen to acoustic waves that are impinging on the glass fiber. The DAS system inserts short laser pulses into the glass fiber. The laser pulses travel to the very end of the glass fiber, and on its way to the end of the glass fiber, it scatters light into the backwards direction of the interrogator. And this backscatter light, this contains all the information we are looking for. So basically the local strain information of the fiber, how it changes over time. Once the DAS system receives the backscatter light, it analyzes the light for frequency, for amplitude, so that we know with what frequency and what amplitude the glass fiber is being deformed, stretched. And it also analyzes the event location so that we get knowledge of where this acoustic event actually happened. And all this DAS systems typically can do with meter level accuracy. So once you have installed the DAS system to the fiber, then and start a measurement, then it will produce data, and there exist many different ways how you can visualize DAS data. A common way to do it is that you create a waterfall diagram of the acoustic energy data. Like the one shown here on the right side, acoustic energy diagram means that basically this chart shows fiber positions that experience high acoustic level, and which are shown here in red color. And then you also see fiber positions that have almost no acoustic energy going on. So this is a typical way of presenting DAS data. However, if you use these sort of plots, acoustic energy, then you lose all the information about the wavefront of the underlying acoustic wave. And this information, this wavefront information, is actually important to many people, like researchers, because they want to study this data. They not only want to know is something going on, but they want to know the details of what is going on. So these are the key points we discussed yesterday. At the end of the presentation, there were two questions where I said it makes sense if I prepare two slides to discuss them better. That's why I will do this right now. The first question was, how can you actually convert fiber attenuation, which I gave yesterday in the form of dB per kilometer? How can you convert this fiber attenuation into linear terms of percentage? So Fiber attenuation means basically that the laser power is being attenuated over distance. So you have to compare the incoming laser power with the laser power after 1 kilometer. So we have to do it with two power levels. And if you want to compare these two power levels, then we are using the definition for decibel for power quantities, which is here presented in the top equation. So the attenuation is given as 10 times the logarithm of the ratio power in, so the initial power divided by the outgoing power. If you now want to convert this into linear terms, so in percentage, for instance, then what you have to do is just divide by 10 and divide by the unit dB. Then you end up with equation 3. The next step is to remove the logarithm. So you bring the left side into the exponent, and then you are left with the ratio P in divided P out. The inverse of this ratio just equals the transmission in percent. And if you know the transmission, then you can calculate the loss, because loss is just equals 1 minus transmission. So if you put in the numbers, then you end up with a loss of 0.045, which equals exactly or roughly 4.5%. So that's the way how to calculate the fiber attenuation in linear terms. The second question was, what is the lowest frequency a DAS system can detect? That is a simple question there, but there is no simple answer because it depends on many things. First of all, of course, it depends on for how long are you running your measurement. The longer your measurement time is, the deeper or the lower the frequency you can detect will be. That's point one. Point two is, what is actually your application? What is the signal you are looking for? Are you looking for a very strong signal? Are you looking for a very weak signal? And that's important because typically for DAS system, the noise increases for lower frequencies. So if you are looking for strong signals, then you might be able to go to even lower frequencies because the signal might be stronger than the noise. If you're looking for a faint signal, then this might mean that you cannot go as low. So that's the first big question mark here. And then, of course, the third point to mention here is what sort of noise level is considered by you as the operator as acceptable. So these are the 3 points that need to be discussed, which are important. And only if these 3 questions can be answered, only then we can talk about what is the expected lowest frequency for a DAS system. All right. So this was about yesterday's presentation. The agenda for today's presentation is shown here. It's actually quite a lot of topics, so I hope I will stay on track with the time. We begin our today's lecture right away with the main topic of it, namely with understanding phase data. That's point one. Once we know the theoretical background of phase data, then I will briefly summarize how phase data can be converted into strain data, because strain is a quantity that is very common in geoscience. After that, we will have a look at how the performance of DAS vendors can be compared. Then it's my opinion that gaining theoretical background knowledge of DAS is important, but I think seeing a DAS system in live action is more fun, and it also helps to understand things better. So that's why I will spend quite some time with DAS live demonstrations. And I will complete the presentation then with a few examples for DAS applications, and I will show you a couple of real-world DAS events. Real-world events recorded with the DAS system. So let's jump into the topic of phase data. I made the experience in the past that whenever one tries to understand phase data, then it is often not clear actually what the term phase refers to. So I think it makes sense first to find a common understanding of the term phase. Here in this presentation, I'm using the term phase in the context of waves. And one of the simplest waves one can think of is a sine wave. I wrote down the formula of a sine wave on the left side, and I have plotted this sine wave on the right side. So in the argument of the sine function, what you see is, first of all, the first term is proportional to x because a wave is propagating in space. And here my space is considered as x coordinates. So we have the first term just describes the propagation in space. And the second term is a constant. This one is called phase. And by changing the value of this phase, one can actually move the sine function to the left and to the right side, depending on the sign of the phase. If the phase is negative, then you are moving or you are shifting the sine function to the right side. If the phase is positive, then you are moving or shifting the sine function to the left side. I have shown here two examples for two different phases of the sine function. So for instance, if we consider a phase of pi over 2, then we are moving the sine function to the right side. The shifted sine function is shown here as green curve. The original sine function is always shown as red curve. And you see that now there is some spatial shift between the two sine functions, which I have called here or labeled here as delta S. And this delta S, this depends on the phase, which is, so you can see the linear relation between the phase shift and the spatial shift in the second equation on the left side. The term phase can also be used for describing how two waves with the same frequency, how these two waves are aligning. So if we consider, for instance, in the third image on the right side, if we consider the two waves, the red and the green wave, then we, by expressing the phase difference between these two waves, we can indicate how well they are aligning. So in this term phase, we will use now in this chapter more often. So that's why I wanted to introduce it. The next point, which is crucial for understanding phase data, is again, and that's why I want to highlight it just briefly, the backscatter light. So why are we seeing backscatter light? I told this already yesterday, but I want to highlight it once more here. In the glass fiber, you find scattering centers. And these scattering centers, they generate the backscatter light that will be detected by the DAS system. If an acoustic wave is now impinging on the glass fiber and deforms the glass fiber, what is going to happen is that the glass fibers, the scattering centers are being moved apart from each other. And this shift of the scattering centers relative to each other is what is causing the signal we are looking for. So just remember this image when we now go to the next slide and dive into phase data. So let's assume a very simple picture. just focus on the right side for the moment. And what we are doing now, we are considering an undeformed fiber section, which is shown here as this blue rectangle. And we are observing how a laser pulse is arriving from the left side. I have now simplified the picture, the laser pulse by assuming that I can draw it as a sine function. That's a simplification here. I just want to mention it, but in reality, it's not quite that. But for the moment, we consider the light pulse as a sine function, which is arriving from the left side. So the sine function arrives from the left side and then arrives at fiber position 1. What is going to happen at fiber position 1 is that there is a scattering center, and the laser pulse now gets scattered by this scattering center. A small fraction of the laser pulse, of the incoming laser pulse, is now being backscattered towards the DAS system. This backscattered light is here indicated by the dashed curve, but most of the light of the incoming laser pulse is moving towards the right side, is proceeding towards the fiber end. So at a later point of time, what is happening is that the incoming laser pulse is now arriving at fiber position 2, which can be some meters to the right side. During that time, the backscattered light, the dashed curve, has propagated to the left side. And now we get a second backscatter signal from fiber position 2, because also there is a scattering center, which now causes backscatter signal. So we are now observing two backscatter signals, the red dash curve and the blue dash curve. And as time elapses, the backscatter light travels to the left side and they start to overlap with each other, which can be seen at the bottom image at fiber position 1. This is when the blue dash curve starts to overlap with the red dash curve. Okay, so what have we observed right now? We have observed the undeformed fiber, how a laser pulse moves through the fiber section, how backscatter light is being generated. So basically how laser pulse interrogates the fiber section. Now, in the next step, we assume that a deformation has happened, and only after this deformation has happened, a second laser pulse arrives and interrogates the glass fiber again. So we are now considering the same fiber, however, which is now deformed. And the deformation is interrogated by the second laser pulse. So we start at the top again. The laser pulse is arriving from the light side. From the left side, it arrives at fiber position 1. We get backscatter signal due to the undisturbed scattering center at fiber position 1. This creates a backscatter signal to the left side. In the next step, the incoming laser pulse moves further to the right side and now hits fiber position 2, which is a bit deformed, so which is a bit stretched to the right side. This is indicated by the vertical dashed line and by the vertical solid line. The vertical dashed line shows the undeformed or the position of the undeformed fiber. And the vertical solid line shows the new position of fiber position 2 due to the external deformation. So what is the consequence of this deformation? The consequence is that the incoming laser light had to travel a bit further to the right side until it reaches this specific scattering center again. Now, this scattering center generates new backscatter light, the blue dash curve, which travels backwards to the DAS system. However, also the return signal from fiber position 2, the blue curve, now needs to travel a bit longer than before until it reaches fiber position 1. And the end result of this fiber stretch is that there is some delay of the blue curve now. And this delay causes the circumstance that the blue dash curve is now overlapping with the red dash curve a little bit differently. This can be observed here if you compare the yellow rectangles, then you will see that the two backscatter signals do overlap differently. And that's exactly how the information of deformation of strain is imprinted into the backscatter signal. So whenever you have a strain on the fiber, the microscopic scattering centers are being shifted. That's why we are introducing phase differences of the different backscatter signals from the individual scattering centers. And this leads to a slightly different signal in the backscatter light. So this phase difference can now be detected by the DAS system. And if you know the phase difference that has occurred between laser pulse 1 and laser pulse 2, then you can calculate by how much the fiber was being stretched. However, there's one important thing to remember is if the acoustic wave which is hitting the fiber is so strong that the induced phase difference is 2 pi or more, then there's no chance to reconstruct the deformation anymore, because then the interference between the two signals or between the individual backscatter signals is not unambiguously, cannot be tracked unambiguously anymore. Okay, I want to make one clarification at this point. I told you that I am using here a simplified picture by assuming a plane wave. Yesterday, I showed you this slide where I was talking about event localization. And I was giving you the two equations for speed and for the refractive index. You need to insert these equations into each other, and then you get the equation on the right side. I just want to point out here that for these equations, I also use the simplified picture of a plane wave. If you are considering that we are actually using a laser pulse, then you would need to use a slightly different formula here. But I would say for introducing the topic, it's a justified picture to use, and that's why I use these two formulas. So coming back to the slide, so we have now learned how strain is encoded into the backscatter light. Now the question is how can we make sense out of this? And for this, I would like to consider the following situation. So I have a DAS system on the left side here, and the DAS system is connected to a glass fiber, which is pointing towards the right side. If we are sending in a laser pulse now, the laser pulse will travel to the right side, the backscatter signal will travel to the left side. And what the DAS system will do is it will sample the backscatter signal so that we know the phase of the backscatter signal for many positions along the fiber. So what we end up is that the DAS system knows the phase of the backscatter signal at multiple sample positions of the fiber. Now what we do is we take two of these samples that have a certain distance to each other. And this distance is called gauge length. So we take, out of these samples, we take two samples that are separated by the gauge length, and we calculate what is the phase difference between these two samples. And this phase difference is assigned to a fiber position, this value. Now we do the same calculation also for other samples. And we assign in that case, we assign the new value to a different spatial sampling. So I'm introducing here two important parameters, namely the term gauge length and the term spatial sampling. The spatial sampling basically tells you how many data points you will get at the end of your measurement. And the gauge length defines you how much space is being monitored by every spatial sampling point. Okay, so that means, yes, in the end, we will have a discrete set of data points along the fiber. However, due to the gauge length, we still monitor the entire fiber. There are no blind spots in between. In the configuration I have shown you here, I have chosen the spatial sampling to be half of the gauge length. That means you will have overlapping regions where the gauge length of the red data point and the gauge length of the what's the name color of the other data point where they are overlapping. So if something happens in between here, where actually I can maybe use the laser pointer. So if actually happens something here, this effect or this event will be shown in the left spatial sampling point, but it will also influence the data to the right spatial sampling point. If you use the configuration I have chosen right now, so that the spatial sampling is smaller than the gauge length. What does it mean? It basically means that you are oversampling your fiber. You can also choose to have the spatial sampling equal to the gauge length. And then you would not have any overlapping anymore. Okay, so this calculation we do for each laser pulse. And then we compare how do these phase differences we have calculated with the gauge length, how do these phase differences change over time? And this is what gives us the phase data. So we are looking at how does the phase difference between two fiber positions, how does this phase difference change over time? Depending on the fiber length, you can have higher or lower pulse rates. If you have shorter fiber lengths, then you can go very high with your pulse rate. And for every pulse rate, for every laser pulse, we are saving all this data. And that means that depending on your measurement configuration, you can end up with a very high data load. For instance, if you have a few kilometers of fiber and you are using pulse rate of 20 or 40,000 per second, then you easily can end up with a data load of tens of megabytes per second. So that means if you're running the measurement for 1 minute, you have already a few gigabytes data. Okay, now that I have introduced phase data, how can we convert phase data to strain? There's not much to explain, actually. So I'm just presenting the formulas. The formulas can be looked up also in other documents. There are textbooks about DAS. There is also a publicly available document from the CFOAM organization, which also gives the formula for converting phase data into strain. Strain itself is defined as the ratio of the length change divided by the original length. If you want to measure this length change with the DAS, then you need to use the second equation. you see the strain epsilon here is proportional to the phase change, which makes sense because the more the phase changes, the more the fiber has been stretched, so your strain is increasing. You will see it also depends on the gauge length, and it depends on a so-called photoelastic scaling factor, this Xi. Basically, this Xi takes care of the fact that if you stretch the fiber, not only the length changes, but also the refractive index. And because the refractive index changes, you need to consider these strain optic coefficients P, and you also need to consider the Poisson ratio nu here. For typical standard single mode fibers, if you plug in the numbers, then you end up that Xi is approximately has value of 0.78. Okay, so having spoken about the strain and about seafoam, I would like to come to how one can compare the dust performance of different vendors. If you want to compare the dust performance from different vendors, it makes sense that you have a standardized procedure for testing dust system, because this will allow you to compare the equipment by numbers and to evaluate whether this DAS system is more suitable for your needs or maybe another one. So it's important to have standardized testing procedures and to look at the standardized testing results. And for this reason, the Seafoam organization has published a set of guidelines how vendors should specify the performance of the DAS systems. In these guidelines, it's mentioned that the vendors should specify their self-noise, the dynamic range, frequency response, spatial resolution, and so on. So that means if you are interested in a DAS system, ask for these numbers so that you can objectively compare DAS systems. So this was now the theory part, and now we are coming to the fun part, which is seeing the DAS system live in action. For this purpose, I have set up a little experiment, actually 2 or 3. And before I'm switching the cameras again, I want to show you the setup of the first experiment. Maybe you remember that in yesterday's lecture, I said that DAS measures local changes in fiber length and that there are different reasons why the local fiber length can change. One of the reasons was temperature. If you heat up a glass fiber, then the glass expands, so you have a local change in fiber length. If you cool it down, then it will compress or will shorten. And for this purpose, I want to start with the first experiment, which focuses on changes in temperature. So the experimental setup looks like the following. We have a DAS system. I have connected a fiber spool of 1 kilometer to the interrogator. After this spool, I have something like 50 meters of another patch cable in between. And in the end, I have added another fiber spool of 1 kilometer. So in total, we have a total fiber length of around 2 kilometers. What I will do now is I will use ice spray. I will apply ice spray on the patch cable to cool the glass fiber down. And I will use a heat gun for heating the glass fiber. And we will have a look at the waterfall diagram, whether we can see a signal. This time, I'm not using an acoustic energy waterfall diagram like yesterday, but we are looking now at a phase waterfall diagram. So we are looking how the phase, we are looking at how the phase of the glass fiber is, oh, sorry, how the phase of the backscatter signal of the glass fiber is changing over time when I'm applying the ice spray and the heat gun. So to that, I need to start the measurement, and then I need to share my screen with you. All right, you should see my screen with the waterfall diagram now. Can you confirm this?
Yes, I confirm. Yeah.
Okay. So just for a brief explanation of the diagram, what do we see at the top? It's a waterfall diagram. The horizontal axis is the fiber position. We have fiber position 0. So at the interrogator on the left side, we have the fiber end on the right side. The vertical axis is showing time again. Everything that is happening right now is popping up on the top and then is moving downwards. The color here indicates by how much the phase of the backscatter signal from the individual fiber positions is changing. What I'm expecting now is if I'm applying the ice spray, then the fiber is contracting. So that means I should see a negative phase difference. So that means a blue signal. If I'm heating up the glass fiber, then I am expanding the glass fiber. So I should see a positive phase difference. That means a red signal. And that's what I will do right now. I just move to the table. So here's the ice spray I'm going to use, and I'm applying it now here on the center of the fiber. Just to let you show, we have the dust interrogator here. I have 1,000 meter of glass fiber here. Then we are going onto this glass fiber here, and I have another 1,000 meter of glass fiber over there. I'm now applying the ice spring. And what you can see is that at the center of my fiber setup, there's turning up a blue signal, so indicating that the fiber is contracting at this area. And that's why we have the fiber deformation that we can see here. Now I'm using a heat gun to heat up this glass fiber section. The heat gun is here. And I'm now heating up the glass fiber. And we see just the another change in the signal with the opposite sign. So that means now we are expanding the glass fiber. So that's something nice to see that DAS, which one of these things can only measure acoustics, can also be used to measure changes in temperature. It cannot be used for measuring absolute temperature, but for measuring changes in temperature. Okay, then the second experiment I want to show For this, I need to change my screen once more. Can you see the original presentation now?
Yes, we do see it, original presentation.
Okay, so my second experiment now will look at proving that we can measure also mechanical, so acoustic deformations. My fiber setup looks like the following here. So I have set up basically I'm using the same fiber setup you just saw in the camera. We have 1 kilometer fiber at the beginning, 1 kilometer fiber at the end. The fiber is taped to the top side of an aluminum bar. And what I will do is I will deform the aluminum bar. And by doing so, I'm actually also deforming the glass fiber. So if I press with my finger the aluminum bar downwards, what will happen is that the top surface of the bar will be compressed, so the fiber will be compressed as well. If I push up the aluminum bar, then the top surface of the aluminum bar will now be under tension. So that means our fiber will be elongated. And these two things are I want to show you with the next experiment. So I'm going to share my other screen again. So if I push down the aluminum bar, then we see a blue signal. Now I slowly go up again. And now I'm pushing on the aluminum bar. And I see that the deformation is just in the opposite direction. So once we have compression and once we have elongation. So this was now a mechanical deformation happening on the low frequency scale, let's say. Now let's happen at mechanical deformations that are happening in the acoustics range, what we are actually interested in. And for this, I am going to use the following setup. I will now quickly rearrange my fiber setup and then use a guitar to generate acoustic vibrations. And this time, the center of the glass fiber setup will not be taped to an aluminum bar anymore, but it will be taped to the top side of the guitar. If I start playing a string of the guitar, then what's going to happen is that the housing of the guitar starts to oscillate. So that means the top surface will start to resonate. You will have mechanical vibrations with very small amplitudes, actually compared to what you just saw. So for a guitar, what I could read in the internet is that if you play a guitar, then the housing oscillates with an amplitude of of around tens of micrometers, so much less than the few centimeters I was deforming the aluminum bar right now. So this is just to show you how sensitive the DAS systems can be. And even these tens of micrometers are generating a very strong signal. So actually, one is much more sensitive than this. For this experiment, for playing the guitar, I will switch, at the beginning, I will switch to an acoustic energy waterfall diagram again. And for this now, I have to turn back to, I have to turn off the laser for a second and then replace the aluminum with the bar. So just give me a second. All right. So then let me switch the screen again. Good. So then let's play the guitar. First of all, again, maybe you can have a closer look. We have the glass fiber here. It's glued to the guitar here. And then we have the fiber termination over there. So if I now play the guitar, then you see in the center of the fiber setup, you see a very strong signal. I can zoom into this. I play it again. Now what I will do next is I'm going to tell the DAS system that I want to have a closer look at the phase data that is coming from this fiber system, so from the guitar. So that's why I will put my cursor right here. Where I could see the guitar signal. And then I will have a look at the Fourier transform of the phase signal coming from the guitar. So here we see the Fourier signal. I have configured it such that it uses 3 seconds of phase data to generate an FFT. And if I play a string now, what you will see is that peaks at lower frequencies will arrive. Yeah. So I'm using right now a pulse rate of around I think 25 kilohertz. So that's why the FFT shows also higher frequencies. But if I zoom into the lower frequency range, where the acoustics is happening, then you see all the higher harmonics from the guitar. And the moment I stop the string, all these higher harmonics are coming. Now, what I will do next is that I want to look how the phase of the backscatter signal from this fiber position from the guitar, how the phase of this fiber position is evolving in time. And what I expect is that since the guitar is vibrating up and down, the fiber will be stretched and compressed periodically. So my assumption is that the phase time series is showing a periodic signal indicating the vibration of the guitar. to that end, I am switching to a different chart. This one here. So what you can see here is now on the horizontal axis, you see time. On the vertical axis, you see how the phase signal from the backscatter light from this fiber position, how it is evolving in time. Right now, nothing particular is happening because there's no much oscillation going on. But if I play the string, then you see we have a massive signal, and you see also the exponential decay of the amplitude of the guitar. Okay, let's zoom into this data and do it again. Let's zoom a bit more into the data. And what you can see here is a periodic signal, which is exactly the vibration from the guitar housing. If I touch the string, the oscillation is gone. So meaning we are really measuring the stretching, the deformation of the glass fiber. All right, so these were the three experiments I wanted to show. Now we are coming to the last part of the presentation, namely DAS applications and DAS data from real events. So since the focus of this DAS course is exploration and mining, I thought I bring some examples here, but also from other applications. So as I told you in the very beginning, the DAS system or distributed fiber optic sensing can be used for many applications. I brought up the example of monitoring railway infrastructure. I also mentioned that we can monitor subsea power cables. You can use it for mining operations as well, for pipeline monitoring. But also you can use it in many other disciplines. And it's not always like one DAS system installation serves only one purpose, but you can actually use the same DAS system for many insights. And one of these examples, for instance, is that you can use existing fibers, for instance, right next to a rail track, of course, for monitoring the train tracks, but you can also use it for doing geoscience, namely for monitoring whether sinkholes are occurring below the train track. Or you can use glass fibers in submarine power cables for detecting earthquakes, which is something we will see on the next slide. So here we have three examples now of real events that were recorded with a DAS system. This chart is a phase waterfall diagram. So that means you can see how the phase of the backscatter signal for the individual fiber positions is evolving in time. And what you can see here is that a vessel dropped an anchor into the sea, and this event was recorded by a submarine power cable which was nearby. The anchor drop you can see here happened exactly at this time, and then you can see how the shock waves from this event are propagating to the left and to the right side along the power cable. And if you zoom in closely, then you end up with this zoom in view on the top right corner, where you can actually see the phase, how the phase is propagating along the fiber. So you can see the minimum and the maxima of the waves propagating in along the fiber. Then another example of real events is, for instance, this phase waterfall diagram, where the DAS system was actually connected to a glass fiber for train tracking, but then an earthquake occurred, and this DAS system recorded the earthquake. The DAS system was installed in Switzerland, but the earthquake occurred in Germany and had a strength of 4.2, and still we could see it with this glass fiber, even though the glass fiber was not supposed to be used for geoscience, but for train tracking, we still could see it in the data. And something very similar happened here. This is data from the submarine power cable. So a DAS system was installed to monitor the power cable for cable faults, but then an earthquake occurred, and we could see the earthquake actually here happening in our DAS data. Okay, with this, I'm at the end of my presentation. I hope the presentation was interesting for you. I tried to show you that glass fibers can be used as sensors for acoustic waves and temperature changes. DAS systems offer many advantages over conventional methods. It provides continuous spatial coverage, real-time monitoring, large monitoring range, but you can also retrofit it to existing fibers. And that's what makes it often so interesting, besides the other advantages, that you can retrofit it to existing glass fibers, and that you can use the same instrument, the same data for multiple insights. We at AP Sensing, we are aware of the fact that the DAS technology is still new to many people, and therefore I want to encourage you, if you are a researcher or if you are a student, and if you have questions about DAS, if you need technical support, or if you see an opportunity for collaboration, then please do not hesitate to contact us. We are always very happy to help and support. With this, I'm coming to the last two slides. I want to say thank you again to Alireza for providing AP Sensing and also myself the opportunity for presenting this introductory lecture to the DAS technology. If you have questions now, just ask them, and otherwise, if you want to contact us, you find the contact details here. Thank you very much.
Thank you, Philip. So before we thank you, we got questions here. So let's just start from the beginning. In the equation you had in slide number 9, there was a term delta S and lambda. Can you tell what they are?
Yeah. Slide 9.
Yes.
Yeah. Yeah. Good point. I should have put the explanation here. So, yeah, lambda is the wavelength of the laser light. Delta S, you can see here, is just the spatial shift of the sine function.
Thank you. So then we have another question. So I think if you go to the formula for phase changes to strain, there's a question there on the CFOM parameters. What are the typical values of those parameters? I think maybe only are left with a refractive index, I guess.
Yeah. So if we go through the different parameters, so lambda is the laser wavelength. So it's typically 1550, so 1550 nanometers. N is the refractive index. Typically for single mode fibers, it's around 1.4682, but depends always a bit on the glass fiber. If you have the so-called ultra low loss fibers, which are used in submarine power cables, then this can be also a slightly different value. GL is the gauge length that can be specified by the DAS operator. It's depending on the measurement configuration, can be 10 meters, can be 5 meters, can be smaller, can be larger. Then this scaling factor here in equation 2, we have the the strain optic coefficients. Typical values for these, honestly, I would need to look them up. I don't know them by heart. Same is true for the Poisson ratio. I only know that for typical applications, so typical single mode fibers, if you plug in the numbers, you end up with an end result of 0.78.
There is a question, why did you use 2 spools of fiber? I think because you were given those 2 spools.
Yeah, I just wanted to make, that's a valid question. I just wanted to make it easy for everybody to see that what I'm doing is is showing up in the center of my fiber setup. I just wanted to have it centered. There's no specific other specific reason.
You got a bit of a praise for the demonstration, so let's go with the questions. How can we obtain measured geographical position of every channel along the DAS cable?
Yeah. That's a very important question. Well, basically what you have to do is you have to do mapping of the fiber to the asset, whatever your asset is. So basically you have you have to map the fiber to the ground. So you need to find the GPS coordinates, how the fiber is routed until the fiber end.
Yeah, and I think, yeah.
Yeah.
Go ahead.
Typically, how you do this is depending on the situation. So many people have already the GPS coordinates of the fiber cable already. So then what you need to do is maybe you walk along the fiber cable, you tap I'm just giving rough numbers. It all depends on the application. Then maybe you tap every 100, 500, or 1,000 meters on the fiber, you're generating a signal. And then you see how where the signal is occurring in your waterfall diagram. So that gives you the fiber position. And then you are assigning this fiber position to the GPS coordinates where you are standing right now.
Good. I was going to compliment you there. Yes, by tap test. Yeah, good. Then can we generate subsurface images from DAS data similar to that of seismics? Seismic application. Can we generate seismic sections from DAS data similar to, I think in this case means geophone-based applications?
Can you maybe elaborate a bit more on that question? Because I'm not a geoscience expert.
I can answer yes, and we will have examples of this in the next types of lectures we have. So, and I think that's the core idea of it. How can we use DAS for subsurface imaging, generating images of what is in the subsurface?
Yeah, actually, yes, you can do it. I can also tell you that, for instance, what we have seen in the past is, for instance, that railway operators, they need to make sure that there are no sinkholes below their train tracks, right? So yes. What they are doing is they use the telecommunication fibers, which are deployed right next to the train track, for doing surface studies. So whenever a train is passing by, the train is generating an acoustic wave which is traveling into the ground and gets reflected by the different layers. So the glass fiber, which is now used by the DAS system, captures the back reflections. And from these back reflections, you can now study whether there are sinkholes below the train track. I think that somehow relates to the question, no?
Thank you for that. Can we use DAS for crustal level tomography? That's for, yeah, so essentially retrieving arrivals and turning them to velocities.
To velocities. I know velocity is now has a specific meaning in geoscience. I think you're talking about particle velocity, right?
Yes, yeah.
So as said, I'm not an expert in geoscience. I think yes, because you cannot. I mean, if you have the phase data, you can calculate to strain. If you have strain, you can calculate strain rate. And to my knowledge, strain rate is then connected to particle velocity.
The answer is yes to this question, Philip. So I don't think it was about conversion to velocity. It's simply we can retrieve, instead of reflection, we can retrieve velocities of subsurface. So you don't have to worry about this. So the answer is yes, and you will have examples of this in other lectures.
Okay.
Then I have actually two questions myself to you. When you were doing the deformation of the aluminum bar, if I recall, when you said that if the deformation is too strong to a point that your phase changes, they exceed 2 pi, then essentially retrieving a strain would be unambiguous, or actually it would be ambiguous. So how much deformation is too much? Wasn't that already not too much when you pressed the aluminum bar?
No, it wasn't, because I chose this speed of my pushing and pulling such that I am within the range.
All right. But there would be a point that if we press too much down, that you basically your phase differences would exceed 2 pi. And then
so basically what you are referring to is the dynamic range.
Yes.
If you're exceeding the dynamic range, then you cannot track back the deformation, and the dynamic range depends on your measurement configurations. So the higher the pulse rate is, the larger your dynamic range is. And that's why, for instance, for this setup, I used a high pulse rate so that my dynamic range is larger.
And then I have one practical question from yesterday concerning fiber optic cables. Since you mentioned manufacturers would like to make, or most clients would like to have fiberglasses that have less scattering centers, so they would have less losses. What kind of info sheet should we look when we buy fiber optic cables? Because as you said, they don't want loss, but we want some loss to get back a scattering of light.
Yeah.
So is that hidden in the refractive index, or where do we look?
So basically, your concern is that your fiber will have too little backscatter signal, or is it? Yes,
or backscattering centers.
Yeah, then you don't need to be concerned at all,
Right.
because these scattering centers I am referring to, these are introduced into the glass fiber during the manufacturing process, and you cannot get rid of them. They are always there. And nowadays, the quality of the glass fibers are actually so good that we reached almost the theoretical limit of attenuation. So basically, what I'm saying is, as long as if your standard single mode fibers are good enough.
All right.
And if you spend a lot of money even for ultra low loss fibers, so that's basically the best you can get, ultra low loss fibers, yes. you have to spend a significant amount of money then. Even those have attenuation of around 0.16 dB per kilometer.
Yeah.
Yeah. So don't be concerned about this. It's rather you shouldn't have too much attenuation, because if you have too much attenuation, then of course the signal will be weaker and weaker the longer you go. But this is I would say for geoscience, correct me if I'm wrong, but to my knowledge, geoscientists, the fiber optical lengths are typically only a few kilometers, right?
At 2 tens of kilometers, yeah. Kilometers to tens of kilometers.
Yeah. So as long as the attenuation across the 20 kilometers is not too high, then you're fine. And that's why I was giving this number. So typical single mode fibers, they offer an attenuation of 0.2 dB per kilometer, some of 0.25. So in that range, yeah. So these are the typical values.
I think this maybe would require another session. None of the lectures introduce engineered fibers with like a helical cables and others. I don't know if you have some words about it, or should we maybe have a lectures on this at some later points?
There's not much I can say about this right now.
Yeah, all right. Philipp, it was a very wonderful lecture. Very much appreciate. I think everyone in the audience appreciated the lecture clarity, and thank you very much. And we look forward for our next lecture, which will be given next week, I believe. So thank you, Philipp, and we'll keep in touch.
Thank you very much. Have a nice day.